in order to, well, so this has, as I explained last time, it's a corollary of the weak-Lefschetz, and the fact that zeta function has, it's a power series with rational coefficients. So this polynomial, this local system satisfies the first condition, right? It has even rational coefficients, but it doesn't satisfy the second condition. But if I twist it by d over 2 and call it f, then, so if I know the Riemann hypothesis for one hypersurface, I take for x0 the corresponding point in U, then the second condition is also satisfied. So, so again, this has rational coefficients. If I twist it by d over 2, I might get some square root of q appearing in coefficients of this characteristic polynomial. If I wanted to stick with QL local systems, then I could, well, I could take the tensor square of this f, if you wish, and apply the theorem to tensor square. But, well, so we can do it for QL bar. Good. So let's start proving. Да. Всегда можно выбрать решетку инвариантную. Если у вас есть компактная группа, действующая на QL векторном пространстве, то всегда существует ZL решетка, которая инвариантна относительно этой компактной группы. А именно вы просто берете любую решетку и усредняете ее под действием группы. Но в том определении QL пучков, которое у нас было такое более общее, QL пучки — это то же самое, что как категория, это то же самое, там объекты — это ZL пучки, а морфизмы — это морфизмы между ZL пучками tensor QL. Так что там это как-то автоматически. Здесь P1 — это конечный предел. Да, это подгруппа в прямом произведении конечных групп. Вот. Very good. So every profiling group is compact, and that's an important fact. So now let's start proving this. So proof of the Kill-Lemma. Step 1. Which is called the ranking trick. So Deligne, in his interview, said that this was the most important trick that he learned from reading a paper by Rankin, as was prompted by Serre. So they worked together on modular forms, and Serre suggested that Deligne should be kind of educate himself by reading some of works of Rankin on modular forms. So that's the following. So let's consider. So I have this. So I have recall notation that I'm going to use. So I have a local system, which is, for me, is a representation of the étale fundamental group in GLV, where V is some vector space over QL bar. So let's take some integer k, positive, then eigenvalues of Frobenius, acting on coinvariance of the geometry of this Frobenius. Another name, Frobenius. This is, I also have, this is arithmetic Frobenius, and the geometric Frobenius is always inverse, acting on coinvariance. So I take V, I take its tensor, 2k tensor power, right? So this is still a representation of this group, and I take coinvariance with respect to the subgroup, geometric fundamental group. Have absolute value equal to 1. Well, so this is a representation of this big group. If you take coinvariance with respect to subgroup, the quotient group acts on coinvariance. And I look at how this Frobenius acts. And this is a very easy statement, because so you have a morphism of vector spaces and here I take coinvariance by 1 u f q bar. And here I have various operators. Well, so this is a representation of this big group. And in particular, I have all this Frobenia for all points x acting here. And in particular, I have my Frobenius fx0. x0 is a special point for which I know that the eigenvalues are all equal to 1 by absolute value. So it acts here. And so I claim that, well, we have this compatibility condition, right? So the action of the whole fundamental group here the action of the entire fundamental group on this coinvariance factors through this quotient. And therefore, in order to compute the action, so I have action of f here, and by functoriality it also acts here, but in order to compute this action, I need to take this fx0, look at its image here, right? And its image here is equal to this element. So it goes to Frobenius q to the power degree of x. Right? So again, on this space, I have the whole action of the quotient group. On this space, I have the action of the big group. But so if I consider this just as a morphism of vector spaces, then it commutes with action of this Frobenius here and this Frobenius here. So now I know that the eigenvalues here are all equal to 1 by absolute value, and this map is surjective, and this implies that eigenvalues of Frobenius degree of x have absolute value equal to 1, right? And therefore, the same is true for the Frobenius itself. Okay, so now here is how we are going to apply it. So k need not be, well, this would be still true if I consider just kth power. It need not be even. but I'm going to apply it to even powers of my local system. So, okay, so this is step 1. Step 2. Okay, so here is what we are going to do. We look at the zeta function of my local system. So with coefficients, so zeta function of the local system, it's 2k tensor power of this local system. So I recall what this is. This is the product over all points of U, closed points, of the determinant of 1 minus geometric Frobenius at this point times t to the degree of this point acting on the fiber, on the stock. Negative. That's the zeta function. And so by, well, we have a formula. So we know that this function is always, for any local system, it's rational. And we have a homological description of the zeta function. It's a corollary that's equivalent to the Lefschetz formula with coefficients in a local system. So what is the formula? So we have to consider the determinant of trace of the Frobenius acting on homology. So on H1 with compact support, we have a curve, right? So we have only H0, H1, and H2. So this is F. And this is the numerator. And the denominator is the product of contribution from H0 and H2. But H0, well, we have cohomology with compact support, right? If I have a local system, H0 with compact support is trivial because we are looking at global sections that vanish at infinity. So H0 is trivial, so only H2 gives contribution. So H2, okay. So this is the kind of our main result that we have proved so far, right? This is the Lefschetz formula. So let's see how. So now I'm going to apply the Poincare duality for curves. Well, I need a special case of this. So
на первом шаге
да.
мы, значит, поняли селективность и куда переходит Фробениус, что это нам это что-то дало про собственные значения.
Фробениуса, да, который действует на этих коинвариантах. А именно же я знаю, что собственное значение вот этого оператора для одного этого конкретного x, x0. Все они по модулю равны единице. Значит, и у этого тоже равны единице. Okay, so now, Poincare duality for curves implies that H2 with compact support of U with coefficients in F, that's power 2k, is the same. Well, it's dual to H0 without compact support of U with coefficients in F, tensor power 2k. dual. This is QL bar dual vector space. And, well, this is just the space of invariants, right? Oh, yeah, sorry, dual local system. Yeah, I need to. The Poincare duality assures that, okay, maybe tensor 2K, and I take the dual local system. That means that simply I take the dual representation, I take invariance in the dual representation, and then I take the dual to the space of invariance. How to express it in terms of representation? So the functor of invariance is dual to coinvariance in the sense that this is the same as just taking V, taking its 2kth tensor power, and taking coinvariance with respect to the fundamental group. Yeah, FQ bar, everywhere is FQ bar, right? We are taking homology with of a curve over an algebraically closed field. So this is pi1 et al. Of UFQ bar. So I hadn't proved the Poincare duality even for curves. And so I will explain. This is a very, very simple argument. And I will explain it at the end. So let's now believe to this, and let's postpone it until the end. I want to use it now. So let's look at this formula. So we know that we have some information about the eigenvalues. Yeah. One important thing is that so how the Poincare duality works. So you have a pairing between this group and this group, and it takes values in H2 with constant coefficients. So this would be true if you. I want to take care of the Frobenius, and if you want to take care of the Frobenius, there is some twist. The dualizing kind of the homology of the second homology of the constant sheaf is Z, is QL of -1. So if you want to take because let's, I need to take this and tensor it with twisted by one-dimensional representation of the fundamental group of FQ, right? So there is this twist here, and I could also write it here. Yeah, so now let's look at this first step. So the first step tells me that the eigenvalues of the Frobenius on this coinvariance are all equal to 1 by absolute value. So that means that here, well, this Frobenius acts here, and eigenvalues have absolute value equal to Q. Now, what does it tell me about this rational function? It tells me that all its poles appear on the circle. So this implies that poles of zeta function are all on the circle, absolute value of t equal to 1 over q. Да, потому что на q от минус единицы Фробениус действует умножением на q. So, okay, so erase something from, yeah, so first step. Now, Okay, so so we have all poles. Well, and this function has sort of no zeros. So it means that what does it mean? So I claim that this implies. So let's now look at this formula here. So this is a power series, right? This is a product of polynomials with so h. So let's look at this formula now. So this determinant of 1 minus Frobenius t acting on the 2kth power of my local system. Yeah. 2k. No, I don't have it. 2k, because I have it here. So let's look at this. So the zeta function is a product over all x of these factors. So this is a polynomial, and I take its inverse. So, so the absolute value of the Frobenius acting on the fibers are real numbers. That means that if I consider the absolute value of the Frobenius acting on the 2kth power, they're all going to be positive numbers, right? Because this is just the 2kth powers of the Frobenius, of the absolute value of the Frobenius acting on this space. So Hess is a power series with positive coefficients, well, non-negative, right? Now, so I know that so this is a rational function. Let's look at this representation of the rational function as a power series. I know that the rational function has no poles inside this circle, inside this circle. So it means that the power series, this entire product actually converges, right? This is Cauchy theorem. So if you have a holomorphic function, its power series actually converges inside this converges inside on absolute value of t less than 1 over q. So every factor also converges on this disk, right? Because well, so what we have here, we have a product of power series with positive coefficients. And we know the convergence of the product on a disk. Now, the coefficients of this power series are bounded by coefficients of this power series, right? So that means that determinant of 1 minus Frobenius x t f 2k x bar inverse converges on the same disk. Right? Now, what does it tell me about the Well, but this power series is very simple. It's this is well, it's inverse to a polynomial. So what it tells me is something about the zeros of this polynomial, right? That this polynomial has no zeros inside the disk. So, that means I will just write the conclusion that eigenvalues of the Frobenius acting on fx bar have absolute value less or equal than q yes, so left behind this number degree x. And also here, degree x. So q to the degree of x square root, well, do kth root of this number, right? Again, because if I have an eigenvalue of this Frobenius acting on this space with larger absolute value, then the Frobenius acting on this 2kth tensor power would have an eigenvalue with absolute value larger than this number, and this would imply that this polynomial has 0 in this disk. So k here is an arbitrary number. It implies, so when I take k go to infinity, I conclude that this absolute value is less than 1. And that's the main trick. So you see, so the original hypothesis was about zeta function of a variety, right? So we take some, maybe with QL coefficients with just constant shift, but we take the product over the variety, over the all points. So here we kind of go in opposite direction. So we use information about the entire product, right? Because it has very simple homological description, and H2 is the group that is easy to understand, to derive information about H factor. So very good. So what we wanted to prove is that all these absolute values are equal to 1. And we proved that there are less than 1. So there is one step. How to show that? So you have an operator, and it has eigenvalues. And we already know that absolute values are less or equal than 1. And you want to show that they're all equal to 1. The idea is to consider the product, because the product is the eigenvalue on the exterior power, on the determinant. So, okay, so what is this? I think it's step 3. So consider the local system L, which is well, determinant of F, and this is by definition the top exterior power, rank F. Right? So Und so fx acting on this L has eigenvalues of absolute value equal to 1. That's what you want to show. And this will complete the proof, right? Because this eigenvalue, well, that's, well, it's a stupid way of saying this. It's one-dimensional space. So is multiplication by a number of absolute value equal to 1, right? There is only one eigenvalue. And this is the product of all eigenvalues we are interested in. So, and this follows from a very general lemma. So let L be a local system, on U of rank 1. Then there exists an integer m such that the action of the entire geometric fundamental group, well, the representation. So what is a local system? It's a representation of the big fundamental group, and I claim that the action of the geometric fundamental group factors through a finite quotient, which means this is trivial for all x, right? So that means that for all x, the eigenvalues of this Frobenius, well, on the Stokes, are all m-roots of unity. And this will definitely complete the proof. So let's try to do this by analyzing what are the local systems, one-dimensional local systems. So да. Но мы уже доказали, что все собственные значения по модулю меньше единицы. Значит, надо доказать, что их произведение равно... Осталось доказать, что их произведение равно единице. Мы сделали вот что. Я еще раз повторю. Значит, мы посмотрели на эту зета-функцию. С одной стороны, мы посмотрели на когомологическую формулу и увидели, что знаменатель не обращается в нуль на некотором диске радиуса 1 кутая. Вот. Это означает, что формальный ряд, который вот в определении зета-функции, вот верхняя формула, он сходится на этом диске. Но как устроен этот формальный ряд? Это произведение по всем точкам У некоторых формальных рядов с положительными коэффициентами. Если произведение рядов с положительными коэффициентами сходится на диске, то тогда каждый из сомножителей сходится на том же диске. Потому что произведение, каждый коэффициент сомножителя, он мажорируется соответствующим коэффициентом произведения. Так? У меня ряды начинаются с единиц. Вот. Это означает, что вот этот вот формальный ряд, он сходится на диске радиуса 1 кутая. А что это за арray? Это 1 поделить на полином. Это означает, что этот полином на этом диске не обращается в 0. Дальше мы перешли к число k, устремили к бесконечности и получили то, что хотим. Very good. So now let's analyze what are the local systems. So by definition, a local system L of rank 1 corresponds to a representation, QL bar representation, and by remark I made at the beginning, so we so QL bar local system is a QL bar representation that has a k lattice for finite extension of QA. So this is actually a representation of pi 1 et al. Of u in some, GL1. So this is just k star. K again is finite extension. That's because it's one dimension. So now, so this has the following structure. It has the Frobenius, and it has geometric fundamental group in it. So this is U, F, Q bar. And we want to understand something about the restriction of this character to this subgroup. So we want to show that nth there exists, this character has finite order. That's precisely the claim. So, so this is an abelian representation, so it factors to the quotient of this group modulo the commutator. And so what can you say about, so I have a character of this group that extends to a character of this larger group. So it means in particular that this character is invariant under the conjugation. So this z hat, this is a normal subgroup. And this is the quotient group, acts here by automorphisms. And it's invariant under the conjugation. So let's put it this way. So let's consider, I will erase this. So what is the structure of the local multiplicative group of a local field? So yeah, maybe even more precise. So I choose a lattice and choose a lattice. It's any there is only one lattice. So it's automatically by continuity it factors through OK. So what is the structure of this group? Well, so I claim that there is a map to OK. And the quotient is a finite group of roots of unity sitting inside K. So to define this map, well, one way to define it is the following. So let's just take the logarithm. So logarithm is defined by a power series, right? So, and I know that it converges in some neighborhood of 0.1, right? So, so there is some, so if my number is sufficiently close to 1, it converges. But if not, let's consider the following function. X goes to logarithm of x to the power n. You see, so for any x here, so there exists a number n so large that for any number here, its nth power is arbitrarily close to 1. Right? So, because what does it mean that a number is close to 1? It means that if I subtract 1, then it's divisible by sufficiently large power of uniformizer. And because the quotient of OK modulo the uniformizer is a finite group by Lagrange theorem, so this will be arbitrarily close to 1, so this will converge. So there is a map, and so the kernel torsion points here, besides the all torsion points, so have this sequence. This is a finite group. Finite group. So we'll prove that home from pi 1 et al. Of U to this group, okay, is 0. There are no homomorphisms at all. Oh, no, sorry. That's not what I wanted to say. So I will prove the following assertion. So let's take, I need to correct it, FQ bar. Okay. So I take these homomorphisms, and inside I take those homomorphisms that are invariant under the conjugation. Okay? So what it means here, so this group is equipped with action of this guy by all tautomorphisms. So I consider only those characters that are invariant under this action. And I know that if I have a character of this large group, then if I restrict it to this subgroup, it will be invariant under the conjugation. So this will imply that any character, any map from this to this, actually factors through z hat. This will imply that, yes, this will complete the proof. Right? Because it's a finite group, so we'll know that the image of this sits here, so it's done. Okay, so now what is this? What are homes from the fundamental group to something abelian? This is just first homology, right? So we want to show that H1 et al. Of U FQ bar with coefficients in OK, and here I take z hat invariance is 0, right? But that's not hard, so because we computed homology, first total homology of a curve. So our curve is a very simple curve. It's just a P1 minus finitely many of points. So I may assume that. So so U is I can write it as P1 minus x0 xn. And so by enlarging my base field FQ, so by making this guy smaller, I may assume that all these points are actually rational points. It need not be the case, but if I prove that this invariants are trivial for a subgroup here, it will imply that this invariants are trivial. So subgroup means that I actually only look at the Frobenius, not the Frobenius, but its power of this Frobenius. And then I may, without loss of generality, so let's... Ну да, давай куштрих. Okay? So, but then, so H1 et al. Of U FQ bar, okay, is simply OK negative 1 to the power n as a module over the Galois group of FQ bar over FQ prime, right? So you see, I remove n points from P1, and every point, so for every point I kind of, this gives me contribution, but the sum of this residues is 0. So I have here n, and here n plus 1 point. Homology of A1 is with QL coefficients trivial. So so we get the result. So this implies that H1 et al. U FQ bar with OK coefficients is 0. And the proof is completed. Okay, so maybe let me use 2 minutes to fill one gap. I want to show that the Poincare duality for curves and only for H2, for local systems. So, okay, so Poincare duality. So it suffices to do it with finite coefficients. So I will prove the following. This is this will be Z mod n Z local system on a smooth curve U. And then, well, n is relatively prime to characteristic. This U is over K. And what I want to show is that H2 of, well, so I will first construct a pairing, H2 of U K bar with coefficients in F, in H with compact support, H0 of U K bar of the dual local system. I want to construct a perfect pairing to Z mod n Z twisted by 1. So, okay, so what is this? This is homology of the Schick extension. So I have U, and I have some compact curve, smooth proper. And this is J. By definition, this is homology of C with coefficients in J lower Schick of this. So I think of this as x2 from the constant sheaf Z mod n Z to oh, no compact support here, sorry. So from this to J Schick of F. And what is this? This is, I can think of this as x1, x0 from J chic F to Z mod and Z. Right? So why that? So I'm taking just home from this sheaf to this sheaf. By junction, that's the same as taking home from F to Z mod and Z. This is X in the category of sheaves on C. This is X in the category also of sheaves on C. So sheaves on C. So this is sheaves on C. And now I can take the Yoneda product and get a map to H2 of C with coefficients in Z mod and Z, which is Z mod and Z twisted by negative. So I constructed a pairing, and now I claim that it's non-degenerate. So in the case when F is a trivial local system, we know the result. It's we computed homology with constant coefficient of with compact support. So in the case when F is just Z mod and Z, it's okay. So okay, if F is Z mod and Z, and because, well, we know that this is one-dimensional, that's also one-dimensional. The pairing is kind of tautologically, this is an isomorphism, we know that. So, so I want to show, reduce the general case to this, and here is the trick. So let's use pick an étale cover U prime U such that pi upper star of F is constant. So then, so I have an exact sequence. So I have F. I have the pi low star of pi upper star of F that maps to F. That's the trace map. Here I have, sorry, so I just want maybe, no, let's not look at the trace map, let's just look at the embedding of this guy into this, which comes by adjunction. And the quotient will be F prime. Okay? So, and now, so homology of this guy is easy to compute because it's homology of is anything of U k bar with coefficients in pi low star of pi upper star of F is just homology of this cover with coefficients in a constant local system. Right? So, and now you use some long exact sequences. So, okay. So here is a sequence that I'm interesting. And so let's. So we want to show that a map from this group to the duo to this, right? From this to duo to this is an isomorphism. So so both are delta functors. So I have H to this compact support of U k bar F. This it's a dual. Then I have H2 with compact support of U k bar with coefficients and this. And I have H2 with compact support of U k bar with coefficients in F prime. Right? So where does it come from? So you have this sequence of shifts. You look at the non-exact sequence of cohomology groups, and then you dualize it, right? You take this Z mod and Z modius, you take home to Z mod and Z. That's an exact functor, because for Z mod and Z modius. So there is no H2, so you have this is it what? Yeah. I think. Let's see. So sorry. So there is no H2. That means that the last term will be. Is it? Ну, третьих, прости, пожалуйста, третьих гомологий нет. То есть длинная точная последовательность, она обрывается. Подожди, но я же дуализировал ее. Я дуализировал, значит, да, нет, я сначала беру длинную точную последовательность когомологии, получаю H2, а потом я все это дуализирую. Значит, у меня заканчивается вот здесь, вот наоборот, у меня вот так вот было. Вот это правильно. Хорошо? Потому что вот это, здесь стоит 0. А здесь все что угодно. Здесь стоит 0. Okay. So now I have an F from this to H0 of U k bar F prime. I have H2 H0 of U k bar this guy. And then I have H0 of U k bar F. Okay? So, so let's prove that this map here is an isomorphism. So this is cohomology of U prime with constant coefficients. And I know that there is the same as, and the same is true here. So, well, so it requires, so we know that these two groups are isomorphic abstractly from the trivial case for U prime. So you need kind of to prove commutativity of some diagrams to show that this trace map that we used here is compatible with this cover, to check that this isomorphism is induced indeed by this trace map. Okay, so what does it mean? It means that this is, I think, injective, right? So I have this commutative diagram. These maps are injective. So that means that this map is injective. All right? So applying, what we already know is that for any, so I made some confusion. So I use this adjunction. Instead, I should have used the other adjunction. So this is also left adjoint to the direct image because this is an entire map. We have this trace map. That's what I should have used instead. This sequence. Да, и тогда будет лучше, потому что тогда будет так, а здесь будут штрихи. Okay? So we already proved injectivity here. For any f, we proved that this map is injective. But then I know that this map is also injective because I could apply the same argument to f prime. And this implies that this is surjective. Okay, so I'll stop here. Thank you.